Okay, let's get our class started here. Some of you weren't here on Thursdays. I just want to mention that week number 1 quiz, everyone received 5 out of 5 points back. I think I posted the grades late Wednesday or early Thursday. Quiz grades are on Canvas for you to see. Are there any questions before we begin? Okay, so today we're going to talk about matrix algebra. And in that, I call it day number 1 quiz. I should have called it week number 1 quiz. In the week number 1 quiz, about 30% of you had said that you do not have any experience at all with matrix algebra. So the remaining 70%, some of you said that you took a Math 314 class here, which is like a whole semester of matrix algebra. But also other of you said, well, I gotten some matrix algebra experience from other classes or maybe some of my research and so on. So we can see we have a wide variety of backgrounds on matrix algebra. So that's why we're going to take about a day and a half here early in the semester talking about what you guys need to know about matrix algebra to be successful in this course. This is not going to be Math 314 in 1.5 days. You don't need to know everything from Math 314, the full semester of matrix algebra from the math department. But what I'm going to do is highlight the stuff that would be important in that class, important for us to understand here. And also you can think of these notes then as a source to go back to as we proceed during the semester with material. Now, why is this important? Why is it important to do matrix algebra? Why can't we just do regular old algebra that we've learned about in other places before if you've never seen matrix algebra? Well, I think it will be clear once we start getting to a little bit of the statistics here, but definitely later in the semester it will be more clear. But just in summary, there are 2 main reasons why we need to use matrix algebra in this course. First of all, the mathematical expressions that we will present will be much easier in a matrix algebra format than not using matrix algebra. And then second, for the computations. Computations are going to be much easier to do, much more general to do with matrix algebra than if you didn't. And you'll see some examples from regression analysis as we go along here today. One of the main focuses then on this section is how to do some of this stuff in R. So while you will be responsible for some by-hand calculations for matrix algebra, like for example, if you've done matrix multiplication, you're responsible for that. But I'm not going to have you do a 100 by 100 matrix times another 100 by 100 matrix by hand. Okay, we'll have R do that for us. If you don't know what that means, you will shortly. Okay, so let me get over here to my notes. So we're going to talk about the basics of what is a matrix. And all that a matrix is a 2-dimensional grouping of numbers in terms of you have rows and you have columns of them. The way that we represent this and then in 2 dimensions is what's shown basically here. Where here I have a matrix that has 2 rows and a matrix that has 1, 2, 3 columns to it. And basically we enclose all the numbers in that matrix with some square brackets. This is a matrix. People will refer to this as a 2 by 3 matrix because there are 2 rows, 3 columns. We can actually write it out, that 2 by 3, like this. This is not 2 times 3, but rather that little x there is meant to be the word by, B-Y, a 2 by 3 matrix. You could have more general size matrices. So if we had, let's say, R rows, C columns, we would R by C. Note that we always say the number of rows first, the number of columns second. That's the convention that's done in math. And we can, if I do specify 2 by 3, we could also call this the size of the matrix. That makes sense. It shows you, well, how big is it? People often refer to this as the dimension of the matrix too. So that's a specific 2 by 3 matrix. Well, we could make this more general. We can start using symbols here. So if I wanted to say that I have some matrix, let's call it A. I would use a bold capital letter to do that. That is the convention. A bold capital letter. Now, sometimes when you're just, let's say, writing stuff out on like a dry erase board, or if I'm writing stuff here out on my surface, I want to emphasize that A is bold. People will put a line underneath it to represent that. So here's my matrix. It is also 2 by 3, but instead of having numbers in there, I have specific symbols. So that when you want to be general in terms of what's inside of it, you use a lowercase letter. So A sub 1, 1 is what's referred to as the 1, 1 element of my matrix. So it's row 1, column 1. A13 is the 1, 3 element. Notice I always say the row number first, the column number second. Okay, one can make this much bigger in terms of, again, an R by C matrix, and that's what I've done here, where people just simply use the ... to mean we're just continuing that same pattern. We will often see what are called square matrices, and that just simply means the number of rows is equal to the number of columns. Okay, so throughout here, we're going to go back to the high school and college GPA example that hopefully all of you saw in the introduction to our notes. Put this into a matrix algebra context so that it has some meaning for what we're doing. Just to review, let me get my introduction to our notes out here. So this GPA data, basically what we have is a random sample of 20 students where we have their high school GPA, we have their college GPA. And what we like to eventually do is develop a regression model that uses high school GPA to predict college GPA. Now, why would you want to do that? Well, imagine if you're working in the college admissions office of some university. You could use then a simple linear regression model that uses high school GPA as the independent variable, or you call it the explanatory variable, or you call it the covariate. Use high school GPA then to estimate, predict what a student will do in college. The college GPA is often referred to then as your dependent variable or your response variable, so that I would have a model that looks something like this. College GPA, I'm going to have predictions of it. We'll put a big hat on top of it. Is equal to beta hat 0 plus beta hat 1 times, call it high school GPA. So the beta hat 0 is the common notation that people use to represent the estimated y-intercept of a regression model. Beta hat 1 is the estimated slope for a regression model. If this by chance is new to you, then you should come talk to me after class, because then I start worrying maybe you don't have the prerequisites for this course. Okay? So we could also put this more in a symbol format where we have, let's say, Y represent college GPA and X represent high school GPA. And so we have a regression model. That's our goal. And we're going to relate this then to, doing stuff with matrix algebra in general. Excuse me. So let's look at our data. So the first observation was someone with a high school GPA of 3.04, and their college GPA was 3.1. The last observation, person had a 2.88 high school GPA and a 2.6 college GPA. Again, we have 20 observations from our population. So what I like to do first, and this is really simple, is start creating a matrix that we would use for regression analysis. I'm going to create this matrix called X. Again, notice it's a bold capital letter. And I have all the high school GPAs, which again was I'm going to call them explanatory variables. That's the name that I like to use the most because it helps explain your response variable. I have all my high school GPAs in one column. Then I also have another column of just ones. Well, you'll see why I put that there too. But we're going to use this X eventually when we do some regression analysis. For those of you who maybe have seen a matrix algebra format here for regression analysis, what is this matrix often referred to as? Does anyone know? We won't necessarily use this term in this class because we won't do much regression, but what is this matrix often referred to as? Especially if you've had an experimental design course. Starts with a D. Oops. Okay. It's called a design matrix. Common term used experimental design, definitely, but it will also be used in regression analysis. Anytime that you are using explanatory variables to try to get at a response variable. So note that this is a 20 by 2 matrix here. Sometimes people will try to emphasize the size of the matrix, especially when it's not all represented, by actually putting right below the letter representing the matrix, they like to put the dimension. Now, a special kind of matrix is a vector. And today we will talk about two different vector is going to mean two different things for us that are closely related, but not exactly. And I kind of alluded to this on last Tuesday. A vector in R's terminology is a little bit different than a vector in math, in what you would see in a matrix algebra class. And we will talk about that difference here. Right now, though, I am talking about a vector in terms of a mathematical context here. And all that a vector is a special case of a matrix where maybe you only have one row or maybe only one column. So an R by 1 vector, an R by 1 matrix, R rows, 1 column, is what's referred to as a column vector because there's just a column. A 1 by C matrix is referred to as a row vector because you just have, let's say, one row of your matrix. And so to denote one of these symbolically, again, we use a capital bold letter. And let's just call it A again for the lack of a better letter out there. And here we have a 3 by 1 vector. It has elements of A1, A2, A3. If I wanted to, I could have put a second subscript there to represent the column, but it's not needed because we know it's just a vector. There's only going to be one column. So in terms of the high school and college GPA, what we can do is put all of those college GPAs into a vector, which we're going to call Y. And again, if you wanted to, you could say this is a 20 by 1 vector. Now, sometimes we would like to change the shape of a matrix, meaning that we like the rows to become columns and vice versa. And when you do that, that has a special name. It's called a transpose. So all of you, probably in a spreadsheet software package like Excel, you've done like a copy paste before where you've changed the rows to be columns and the columns to be rows. You specify the transpose way to paste the information that you highlighted in cells. Well, we can have a transpose of a matrix here. So here's my A matrix that we have before written in terms of symbols. Then if I put this row as the first column. If I put the second row as the second column, voila, I have a transpose. So notice how the transpose of this matrix is now 3 by 2 in size, or in dimension. Now the symbol that we often use to represent a transpose is if we put it like a little apostrophe on the original letter that we were using for the matrix. So, excuse me, and the way that this is vocalized is usually as A prime. So that little apostrophe or that tick mark is actually referred to as a prime. So A prime. A prime represents the transpose of A. So again, with the high school and college GPA data set, we can take that column vector of the height of the college GPAs, we could transpose it, and it becomes a row vector. Okay. Well, at least so far, I don't think that this is too difficult. I have to admit that this is one of the few times where I spend the whole class period talking about math rather than statistics. Well, pretty much rather than statistics. So I know you're all here for statistics, but we need to go through some of this. Let's start doing some mathematical operations then with these matrices. So if you have two matrices, you can add them together or you can subtract them as long as they're the same size, the same dimension. So if I have two matrices, A and B, that are both 2 by 3 in dimension, if I were to add them together, you do what you kind of would expect to do. I take the 1 that's in the 1, 1 part of A, add it to the -1 that's in the 1, 1 part of B. What do I get? Well, 1 minus 1 is 0. We have this 3 here. I add it to the -1. Of course, I get 2. And so what we're doing here is what's referred to as element-wise operations. Just a little bit more of a fancier way to say what we're doing here. Each element in one matrix has this mathematical operation applied to it to the corresponding element in the other matrix. It makes sense to do that. Okay. Subtraction works in the same way. So let's talk about how we can now do some of this stuff in R. Okay, so here's my editor of choice, 10R, to do this. Just to confirm, is the font big enough so all of you in the back row can see it? Okay. So the first thing that we need to do is tell R, I have a matrix that has certain elements into it. So we're going to create this A matrix that we've seen before. And so, for the lack of a better name, I'm going to call this object in R A. A gets the results from a function called matrix. Now, the first argument of matrix says, what am I going to put into it? And since in statistics we typically deal with data, well, the argument name is actually called data. So I'm going to put in there 1, 2, 3, 4, 5, 6. And notice how I've used the C function, which we saw on Tuesday, which stands for combine, or actually officially concatenate. I'm going to put those 6 numbers together into one form. Excuse me. And that's going to be my data. Now note that, so if I wanted to, I could, let's say, highlight that segment of code, run in R, and we can see that indeed everything's together into one form. Okay? Now I actually purposely hit enter there so that you can see better how the matrix is going to be formed. Again, we're going to have this 2 by 3 matrix, 2 rows, 3 columns. And so I specify the number of rows as 2, number of columns is 3, and then I have one last argument that's called by row. By row equal true. All that tells R is, let's put these numbers by row into my matrix, meaning I'm going to have the 1, 1 element be 1, the 1, 2 element be 2, the 1, 3 element be 3. Now I go back down to the next row. The 2, 1 element is going to be 4, and so on. So I'm putting everything in. I'm filling up the rows first. And so if I highlight that code and run it, there we go. There's my matrix. Notice how R puts some other information around there. So we can see square bracket 1 comma square bracket representing, hey, this is row 1. Here's row 2. Here's column 3. So let's say if I wanted to pull out the 6 from this matrix. How do you think I would do it? How could I extract it from A? Exactly. So this is, one of the ways that we saw about how to work with a data frame, where you can use basically the rows and the columns, put the corresponding indices in there to pull the stuff out. If I just did, let's say, A bracket 2 comma N bracket, I just get row 2. If I did put a comma 3 in there, I get column 3. Okay? Now, something that's very important for you to take notice of is this by row equal true argument. The default is actually by row equal false. So if I type false instead of true there, or if I just simply deleted it, look what's going to happen. It puts the data in by column. So it fills the first column first, the second column second, and so on. That is the default way that this is done. And so this is one of those places where students can get tripped up, where they forgot to put the by row equal true when they wanted by row equal true. I always like by row equal true because it helps me better see how everything is going in based upon how I've entered it in my code. I wish they would make by row equal true as the default, but they don't. Now, why do you think I had to put all this, I had to use the C function here to combine everything in that data argument, and instead, suppose I would have had this. Why do you think I needed to do that in my code? Well, let's see what happens. I haven't run it before. Uh-oh. It's giving me some errors. So in our syntax about how it does stuff, note that it separates arguments by commas. And if I would have just simply put data equal 1 comma, then it would think, okay, my argument has ended. And then whatever, if you look in the help for matrix, whatever is listed next as the next argument is going to give it a value of 2. Whatever next for the next argument is going to give it a value of 3, and so on. That's not what we want. So that's why we need to actually combine together the data into one form first and put that all in the data argument. Now, every object in R has a class. We actually mentioned that last time. Oops. And A has a class called matrix, which kind of makes sense. Once again, an object doesn't have to have exactly the same name as the function that it came about. It's just the person who originally programmed the matrix function R decided to give it a class called matrix because it made sense. You can actually have multiple classes for an object. We won't need to worry about that here, so I'm just going to move on and not worry about this array part here. So I can also create the matrix B as well, and let's do A plus B. Oops. And notice we get exactly what was in the notes. So again, the 1 plus a minus 1 is a 0. Okay? To do the minus, we can just do the minus there. Okay, let me swing back to Word to make sure I talked about everything that I needed to there. So sometimes in my notes, you'll see stuff I've typed in red. This is usually when I'm, the day before I go through, I typically go through what I'm going to say in class in my head, and I might be thinking, oh, I wish I would have also put that in there. And so the first thing in red was how do you access parts of the matrix? We already talked about that. The dim function in R, which is not something that I mentioned in the notes. So if I have, let's say, dim A, oops, this gives me the dimension or the size of the matrix. I'm going to use that function coming up. That's why I wanted to introduce it here. So the row is first, the column is second. Okay, let's talk about a vector then. So I'm going to create, first of all, in a mathematical context, a vector in R. And the way to do that is to use the matrix function. And let's say this vector is just going to be a simple column vector that has the numbers 1, 2, 3 in it. So number of rows 3, number of columns 1. And I don't need this, I guess, in this particular case, by row equal true. And if I take a look at Y and also the class, we can see that indeed it is a matrix. It is a matrix type, but it's a vector since it's since we only have one column. Now, what I mentioned earlier, and what we talked about a little bit on Tuesday, is that R refers to, if I use this C function and combine, let's say, the numbers 1, 2, 3 together, R refers to that in its terminology as a vector. So let's look what happens when I do that. Okay, so we can see X does have 1, 2, 3 in it. And you might be thinking, oh, it must be a row vector. Actually, it's not. So look what happens if I did dim with it. If I did dim with Y, I do get what I want. So what R treats is what it calls a vector is just some way of putting numbers together into one object that doesn't have a certain number of rows or a certain number of columns. That's R's definition of a vector, which is a little bit different from the mathematical definition of a vector. And in fact, if I were to say class of X, notice it's not going to come back as matrix. Instead, it says numeric. Now, indeed, in R's terminology, this still means it's an R vector, and so there is a function called is.vector. And if I were to use that with X, it will say true. And indeed, it is a vector. So shortly, we will talk about why this little part that I'm highlighting here can cause some confusion than when doing some matrix algebra calculations. If I want to do the transpose of matrix, I use a function called T. So T of my original A indeed does give me my transpose. Okay, any questions? Next, let's talk about matrix multiplication. The first part is going to be easy. I'm going to define, first of all, something in math called a scalar quantity, which is simply a 1 by 1 matrix. That's all. So it's like the number 3 or the number 10. And let's say I want to multiply a matrix by a scalar quantity. And if I do this in a symbolic way, where let's say that C is my scalar, and I take C times A. If one wanted to, you could say C dot A, but people will often just simply write the letters right next to each other to mean multiply. Then what happens is essentially I take C into every single part of my matrix and do the multiplication. That's it. So if I have my usual A matrix and C was 2, we can see that indeed 2 times, let's say 2 times 6 is 12. Now where things get a little bit more complicated then is when you have 2 matrices and you want to multiply them together. We will frequently want to do matrix multiplication in this class. And so to represent this symbolically, let's say I have 2 matrices, A and B. And if I want to say A times B, I can just simply write the letters together like that. You could also do A dot B. I'm okay if you want to use an asterisk too to mean matrix multiplication, because that's often what we use to represent multiplication. You might be thinking, oh, of course. A story I always like to tell my students whenever I teach this is that my very first semester of grad school, I actually typed up my first homework assignment and I had like A asterisk B to represent I was multiplying 2 matrices together, and the teacher took off points for that. Because asterisk is not really multiply, it's just a convention that we have because there's not a good multiply symbol on a keyboard. I did get the points back though. But notice I do not say A, that little x, B. Why? Because x, we've used x to represent the word by, by, when I'm talking about dimension of a matrix. So I will avoid doing that. Now, I guess if you're coming into multiplying matrices totally brand new, you've never seen this before, you're going to see some quirks here. First of all, in order to, let's say, multiply A and B, that matrix on the left has to have a number of columns that's equal to the number of rows for the matrix on the right in order to actually be able to multiply 2 matrices together. So what that means is that not all matrices can be actually multiplied together. It's only when this special property holds true. So for example, if A was 2 by 3 and B was 3 by 10, I can do the matrix multiplication because those 3's match up. Then you might be wondering, okay, well, what's the final dimension of the resulting matrix? Well, that's where you look at the number of rows for the matrix on the left and the number of columns for the matrix on the right. So in the end, the resulting dimension of A times B, and we'll call the result C, is 2 by 10. In a very general manner, we can write it like this. Notice how these Z's match up. Notice how I have a W here, W there, and I have a Y there and a Y there. So let's actually look at how the mathematical operation of the multiplication works out. And I'm just going to show you through an example. So we have our A matrix that we've seen before. I've changed B. Notice that A is 2 by 3. B is 3 by 2. Notice how the 3's match up. So that means I can do the multiplication. The end result will be a 2 by 2 because of these 2 things there. Now, to do the matrix multiplication, what we do is we take the first row of A and we basically multiply it by corresponding elements in the first column of B. We do what's called in math a cross product, where I take 1 times 3, 2 times 1, 3 times 0, and I simply add the result So I have 1 times 3 plus 2 times 1 plus 3 times 0, which ends up being 5. Since this was row 1 and this was column 1, the end result is the 1, 1 element of the matrix that we find. So we can do one more quick example. Let's look at how I found this 16 here. What I did was I took the elements in row 2 of A times the elements that are in column 2 of B. I multiplied them together and I summed them up, and that's how I get 16. Now, this mathematical operation, I could ask you on a test to simply do it. That test number 1. But again, I'm not going to do a large matrix. And I might just say, give me the 1, 2 element of the resulting matrix, just to save time. Show me how it's done. After test number 1, most of the time what we will do is actually simply have R do the calculation for us. But it's still important for you to understand the math of what goes into that calculation for what we're going to be doing in the semester. So that's why I could ask you a question about that. Now, back when you first learned about multiplication in elementary school, you learn that 2 times 3, which is 6, is the same as 3 times 2, which is 6. However, when you're working with matrices, unless special circumstances occur, A times B will not be equal to B times A. And a quick way to think about why, well, look at here's B times A. The final result, since B is 3 by 2 and A is 2 by 3, the final result is a 3 by 3 matrix in the end, where when I did A times B, I had a 2 by 2. So, yeah, they can't be the same if they're a different dimension. And here I just kind of wrote out more in symbols what's actually going on. Okay, so let's talk about how we can do this in R then. So I'm going to create my matrix A. I'm going to create my matrix B. So here's A, here's B. Now I want to multiply these matrices together. If you're coming into this completely brand new, you might be thinking, okay, well, just do A asterisk B, just like what we did for A plus B or A minus B. Fortunately, it doesn't work. That's not how you multiply matrices together in R. I'll show you what this is actually doing and why the error comes up shortly. And instead, if I want to multiply 2 matrices together, I need to use the following syntax. A percent asterisk percent B. And there I get my result. I can do the same thing as well for B times A. That's how I get it. It's common in software packages, but not necessarily all software packages. They will use different symbols for matrix multiplication. So it's not just R that's like this. Well, what will be actually done if I just only use the asterisk? And to do that, I'm going to create a new matrix, which I call E. It's just going to be exactly the same as A. Okay? And if I were to take A asterisk E, this is what I get. Remember before when we were talking about addition, where it was element-wise operations? That's what the asterisk does, element-wise operations. So what's going to happen here is, for example, in the 2, 3 element of A, which is 6, the 2, 3 element of E, which is 6, it's going to multiply them together to get 36. That is not matrix multiplication, though. So be very careful about that. I've seen students put an asterisk there and wonder what's going on wrong. It's because of that. Now, why did I get this error here, non-conformable arrays? What that basically means is that if I'm doing element by element multiplication, I need the two matrices to be exactly the same dimension. And when we originally had A and B up here, we didn't have them the same dimension, so that's why I said non-conformable. The word array comes about because a matrix is actually a special case of something called an array, which can have more than two dimensions. Okay, now let's talk about working with vectors then. So in R's context, let's say again I have this vector x that contains 1, 2, 3 in it. Again, we don't know what if it's a row vector or column vector. It just has 3 numbers, this object. And so if I did a percent asterisk percent x, A is a 2 by 3 vector. I'm sorry, 2 by 3 matrix. How does R know what to do then? Because x is not a regular old mathematical vector. Well, let's look at the final result. It does return an answer. What it does is this. It says the only way that this matrix multiplication works is if I make this x a 3 by 1 vector. And so what R does is it says, okay, let's promote this to an actual 3 by 1 mathematical vector so that A can be multiplied by x. That's what happens. So, in other words, 1 times 1 plus 2 times, 2 plus 3 times 3, you get 14. Now you might be wondering, okay, well, let's say I have 2 of the, yes?
For example, when we use that, because I tried to do the opposite, x times 8, and it gave me like a non-conformal argument, and we use that, like the percentage symbol in the times, we always change it the second time.
No, thank you for bringing that up. So the problem is, there's not a way you can do this at all, because the number of rows of A is 2. So you cannot have a 1 by 3 vector or a 3 by 1 vector out in front of it to make it work. That's why you have the error message. Thank you. But how about we did this? X percent asterisk percent X. Let's see what happens. I get 14. So what it did was, again, take a look at X here. What it did was it made this first X a 1 by 3 vector, made the second X a 3 by 1 vector. Well, why? Let me go. This is directly from the help for percent asterisk percent. What happens is it uses what's called an inner product in mathematical context. Inner product is going to give you a scalar quantity in the end. And so that's why it made these objects match up in this way. So it was 1 by 3 times a 3 by 1. R uses inner products. Now, alternatively, maybe R would have instead done. Let me get back here. Maybe here's my X again. Maybe the X, the first X, should have been 3 by 1, and the second X should have been 1 by 3. You could do that. You get a 3 by 3 matrix in the end. How could you tell R to do that? Well, use what's called an outer product. And that will be the very last time that you'll ever see an outer product in this class. But it's a common question that I have. Well, how could you do the other opposite way? Okay. let's go back to the high school and college GPA data set. We're getting closer to be able to do some regression stuff with it. So I have this X matrix with this weird column of ones out in front in the first column of X. I have my Y vector here. What I want to do is find a few different quantities, such as, this is how people would vocalize this, X prime X. You could say X prime times X if you want to, but most people just call it X prime X. X prime Y I want to find Y prime Y as well. So to do this, I should mention this just to make sure that this is clear. This was in my introduction to R notes too. Every example that I have has a title to it, and if there is a corresponding program with it, I put that in parentheses. And also, I unfortunately deviated from my convention here. I always will put the corresponding data set name as well, so that you can go ahead to go to my website and find the program, find the data set. Okay? I'm going to go ahead and put that in red there. Okay, let's see here. No, I don't want that. Okay. As discussed in the introduction to R notes and what we did a little bit last Thursday, there are multiple ways to get data into R. The way that I primarily will use in this class, my favorite way, is what I'm showing here. And that is, I happen to have a folder on my computer that has my data set installed in it. I know what that folder is. It's simply on my C drive of my computer. It's in the data folder. It could have been someplace else. It's just that's where it is on my computer. My data set is called gpa.csv in terms of the actual file name. What does it look like? Let's see here. It's a comma delimited file. That's what the CSV represents, comma separated values. And here it is in simply a notepad on my computer. And we indeed do have the columns separated by commas. So the easiest way to read in this kind of a file is to use read.csv. I put that in an object called GPA. And whenever I read in a data set, I always use the head function with it so that I can look at it to make sure it was read properly. Now, there's 20 different observations in this data set. I'm not going to look at all of them. The first 6 should be enough. If I wanted to, I could also use the tail function to look at the last 6. If I want to be extra careful, I could say, GPA, head GPA, comma, n equal 10 to look at the first 10. We'll have much larger data sets this semester, so I often just go with the defaults, look at the first 6 observations to make sure that they make sense. Make sure everything was read in properly. So there's my data. Now with this then, I need to first find my X matrix. So I'm going to create an object called X. It's going to get the results from a function called cbind, which stands for column combine. I'm going to combine the number 1 for the first column with all my high school GPAs. And again, the way that you can extract information from a data frame in terms of variables, variable values, is to use that $sign. So GPA, $HS GPA gives me all my high school GPAs. In R's terminology, this is a vector as well. Now, I'm going to, again, combine it with that 1. I want that leading column of 1. So if I execute that code and run it and take a look at X, there we go, my 20 by 2 matrix. Now you might be wondering, well, wait a second, Chris. There's only one 1 here. There's not 20 ones. How do you get 20 different ones listed there? Well, this is a nice thing that R does. R uses what it refers to as recycling. It recycles the numbers, in this case the number 1, enough times so it matches up with the number in the other column, which was for the high school GPA. And so it makes it much more convenient rather than me typing 120 different times. So there's my x. Here's my y. I'm going to pull out college GPA from my data frame. That is also a vector. And now let's do some math. So the first thing I want to do is take the transpose of x times x. Let's go ahead and do that. And this is what I get. But let's take a look at this now back in my notes, see what's actually being done. So let's actually write out what x would look like and write out the x prime x operations. So in a very general format, I have, I have a column which I have x11, x21, and what is that? Well, that's just simply the ones. Okay? My second column contains the high school GPAs. Symbolically, would be like x12, x22, and so on. Again, the first number in that subscript is the row number. The second number in that subscript is the column number. When I take the transpose of x, this becomes the first row. The second column of x becomes the second row. Now, when I do the math, do the matrix multiplication, I'm going to take this column of ones, this row of ones times this column of 1 and add each corresponding multiplication that does. And look what I get. 1 times 1 plus 1 times 1. If n was, let's say, my sample size, just to be general, rather than putting the number 20 there, I would have n. Look what happens when I take this row of ones times this this column of x's. I get the sum of all my x's. Look what happens when I take these x's with these x's, row 2, column 2, I get the sum of the x's squared. Okay? Now, why is this important? Well, let me go to the notes of another class. So this is directly from my Stat 801 notes. And actually, I use this as well when I taught 380 before, when I taught a version of 218 before as well. When I taught Stat 450 and 870 before. So it's not just 801, but this is from my Stat 801 notes. So with our regression model, we have y hat is equal to beta hat 0 plus beta hat 1 times x in a general format. X is the explanatory variable, y is the response. Now, to find this beta hat 0, this beta hat 1, we use what's called the least squared method. We get least squared estimates. All of you should have seen this before. All of you should also have seen corresponding equations before for these least squares estimates. Notice here, sum of the x's squared, sum of the x's, sum of the x's. We just got those from doing some matrix algebra as well. Okay. Now let's go back to my R program. Let's look at the transpose of x times y. The transpose of y times y. Here are the actual results. If we go back to my original set of notes, look at what happens symbolically then. So if I have x prime times y, the end result is the first element of the resulting vector is the sum of the y's. Also, the sum of the x's times the sum of the y's. This is the second element. Look at my Stat 801 notes now. Sum of the x's times the y's, sum of the y's. All the stuff that you need to get beta hat 1. very shortly, I'm going to do one more step and show you how automatically then we can do this calculation without that form that you've seen for equations before, but instead using matrix algebra. Okay. First, though, we're going to look at some special types of matrices that will pop up for us. First of all, something called a symmetric matrix. All that means is that if you have A as your matrix, if you take the transpose of it, it's exactly the same as A. It doesn't change. That's a nice little thing to have occur. Do note that matrices need to be square for this to occur. Because a 2 by 3 matrix, when it's transposed, is 3 by 2. Obviously, it can't be exactly the same. So that's why it has to be a square matrix. So here's an example. This is a new version of an A from what we've seen. This is a symmetric matrix. So notice the 1, 2 here becomes the 1, 2 there. And in the end, the matrices are exactly the same. Now, when the row number is equal to the column number of a matrix, in terms of like the element, so like the A11 element, the A22 element. When the row number is equal to the column number, those corresponding values there are referred to as the diagonal of a matrix, because it kind of is a diagonal inside the matrix, based on what I just circled. All the other elements of the matrix, such as this one here, such as this one there, are called off-diagonal elements. And so we could have a bigger matrix, such as this. Let's see here. So here I have a 3 by 3 matrix. The diagonal elements are what I'm going to highlight here in orange. The off-diagonal elements then are highlighted in yellow. Notice for this matrix, the 2's match up, 3's match up, the 5's match up. This is a symmetric matrix. So in other words, for example, the A1,3 element is equal to the A31 element. Now at times, and this does happen a number of times, otherwise I wouldn't be talking about it, you might have a matrix that looks like this. It's a diagonal matrix where all the off-diagonal elements are 0. This can actually be very advantageous for us in I guess I'll just say right now in the simple context, let's say if you wanted to multiply the matrix A times something else. Well, think about how much easier it will be able to do the multiplication when you have zeros. That special format then can be taken advantage of in certain situations. Now, even more special case of a diagonal matrix is when all these elements on the diagonal, let's say that they're equal to 1. Then we have what's often referred to as the identity matrix. Most people just use the letter I, not the number 1, but the letter I bolded to represent an identity matrix. This has a special meaning for us. So again, in elementary school, when you learn that you have, let's say, 3 times 1, you get 3 back. So essentially 1 identifies what you're multiplying by. Yes?
So in order to a matrix to be classified as identity or the diagonal, the number of rows and columns should be equal.
Yeah. So notice that these matrices are symmetric, and so that's where we get that. I just didn't carry it through. Yes?
So the identity matrix also has the requirement of getting zeros as those diagonal?
Yes, yes, yes. So basically, an identity matrix is a special case of a diagonal matrix, except for the diagonal elements are 1. Now, the reason why I brought up this 3 times 1 is because the identity matrix essentially gives us the same thing in matrix algebra. So if I take A times I, where they're appropriately sized, I get A back. And with these kinds of matrices, then I can take I times A and get A back as well. The identity matrix will pop up a number of times for us this semester. At times, you might want to have a vector of all just one number itself. And the convention is, if you want to represent that symbolically, is put the number in bold, and therefore meaning that you have, in this case, a vector of zeros. Okay. Let's talk about now the inverse of a matrix. So we talked about the equivalent, let's say 3 times 1 is equal to 3. Now let's say if I have 3 times 1/3, I get 1. Or if I have 3 times 3 raised to the negative 1 power, I get 1. So essentially, this here is the inverse of 3. Well, now what's the equivalent then for matrix algebra? Well, in a symbol format, if I have, again, a matrix A, if I have A raised to the negative 1 power, that means that's a symbol to mean inverse. A times A inverse is the identity matrix. Just like how I had the number 1 there. I can also, since I'm excuse me, I should say that we are dealing with a square matrix. I could also have A inverse times A, and I will also get the identity. Let's take a look at an example. So here's A, and I've already calculated, and I'll show you how to do this shortly, A inverse. And so if I took A times A inverse, you can go through the math on your own, I do get a 2 by 2 identity matrix. Now, how do I find this? Well, for a 2 by 2 matrix, there's a nice little formula that you can use to automatically get the inverse. This is how it works. So let's say that A is now a 2 by 2 matrix. And what I do is I flip the 1, 1 element and the 2, 2 element. I flip their positions. And then I put a negative sign on the off diagonal elements. And then I do one last thing. I multiply by a scalar out in front, which is 1 over A11 times A22. In other words, take the product of what's on the diagonal minus the product that's on the off diagonal. If you go through all that, oops, I'm running out of room. You go through all that, you get the inverse for that specific case. You can also find inverses for larger matrices. You are not responsible for that other than through using R, as what we will see here. Although I'll just use the 2 by 2 matrix as the example. Okay, so I'm going to form my A matrix. Again, this is a little bit different of A matrix than what we've seen before. And to find then the inverse, I use not the inverse function, because there isn't one in regular R. I use the solve function. And there's my inverse. So just to verify that indeed this is an inverse, I should get the identity matrix back if I take A times A inverse. So let's do that. And that's what I get. So I have 1 here, a 0 here. We have 1.0000 times 10 to the 0 power. Well, that's 1. Then I have 1.11 times 10 to the negative 16 power. Oh, it's not exactly 0. It's close enough, though. Okay? see here. So why is the solve function used? It's not going to, or why is it called solve versus the inverse function? It's not really relevant in our class. If you're interested, especially if you've had a matrix algebra class, you can take a look at that stuff that I just highlighted there. Okay, now we go back to the regression example with the high school and college GPA. Here's our X matrix. Here's our Y vector. I want to find two different things. X prime X, the transpose of X times X, invert the whole quantity. So notice how I put a parenthesis around that whole quantity before I put the -1. Also, I want to find X prime X inverse times X prime Y. Now, if you've taken a full-blown Stat 450 or Stat 870 class, you will have seen this a lot. I know when I took my first class like this, our professors made us recite over and over again out loud during class, X prime X inverse X prime Y, X prime X inverse X prime Y, because it's so important. Okay, so let's see why it's important. I'm going to come back over here to my R program. So, transpose of X times X, which we've seen before. I can enclose all that inside the solve function to get transpose of X times X, that quantity inverted, or in other words, X prime X inverse. Now, let's combine that with multiplying by the transpose of X times Y. And this is what I get. 2x1 vector. You should verify that indeed that you would get a 2x1 vector by just looking at the dimensions of the corresponding matrices that you're working with there. Now, why is that important? Well, back in the introduction to R notes, we actually estimated the regression model. We found beta hat 0, we found beta hat 1 using the LM function, where we said formula equal, this is where you specify the model. Here's my response variable, tilde, here's my explanatory variable, data is in GPA. I put them into an object called mod.fit. And if I just say, I want to see what's inside the coefficients part of the list that's mod.fit, this is what I get. Notice this is exactly the same as what we just got from doing those matrix multiplication. So X prime X inverse times X prime Y gives you your regression estimates. Your beta hat 0, your beta hat 1. This is how this kind of stuff is actually programmed in not just this statistical software package, but others as well. It's done through using matrix algebra. Now, why is that especially useful? So you might be thinking, well, I could just simply program in the equations that you had before that you posted from Stat 801. Well, let's say that I had another column there. Suppose in addition to high school GPA, I had another variable that was number of high school activities. And I had that as another column for a second explanatory variable in my model. And I would just add another column to my X matrix. Suppose I had another variable such as ACT score. Put that as a fourth column in my X matrix. Does anyone know what beta hat 1, beta hat 2, beta hat 3 are for a regression model in this situation? An actual equation for it? No. That's not taught. Instead, I can still simply, with my adjusted X matrix, use X prime X inverse, X prime Y, and find the corresponding regression estimates, the beta hats. The equations don't change. Just the X changes a little bit. That's why people put all this in a matrix algebra context once you get beyond an intro stat course. Okay. So this next part of the notes, linear dependence and rank of matrix, we will talk about that another time. Let's see here. Let's quickly do this next part, and then we'll end it. So there's other mathematical operations that one often will do with matrices. One is to find what's called a trace of a matrix. Very easy. Sum the diagonal elements. That's all. The symbols that people use with that is they typically use TR for trace, parentheses, the matrix, and parentheses. That's all. Okay? Now, there's actually not a function in R that finds a trace of a matrix. So you have to kind of do it yourself. As I have here, what you should do for practice, write your own function that does it. Let me come over here to R. So let's say I have a matrix A again, and it's this simple version of A. Now, to find a trace of a matrix, you do need to continue to have a square matrix. And to find the diagonal elements of A, I can use a function called diag, D-I-A-G. And notice how it pulled off the 1, 1, the 2, 2 elements. Then, to find the sum of that, which is the trace, I can find just the sum like that. Use the sum function. It sums what's up in there. Okay. Actually, I'm going to stop right there. And before we go, let's take a look at something else. So first of all, I will say that this is what will hopefully be the boringest class period of the semester. You know, going through all these mathematical details, the definitions and stuff, it's just something that we need to do. And so I do it all at once, and then we'll come back to some of these things as a reminder throughout the semester. It will get more interesting once we start looking at data and actually analyzing it, applying some of these matrix algebra techniques to help us do that. Okay, so what's next in our class here? Well, I have my office hours after class. On Wednesday, you have the week number 2 quiz due. That mostly is over the introduction to R stuff. It's not the matrix algebra stuff. That will be week number 3 quiz. Please make sure you get it done by 5 p.m. on Wednesday. Then on Thursday, we will finish the matrix algebra section. I don't know why I have a question mark there. We will finish it. Then we will start doing the data distributions and correlations section. Probably the most interesting thing that we will do then in that section, at least on Thursday, is that we'll define 3 different data sets that we will be using throughout the semester. And I'll be posing some questions that we want to answer from those data sets. So what I recommend that you do is you have my data distributions and correlations set of notes with you, either on your laptop so you can take notes on them, or simply print them off and take notes on them by hand. Next week, then, we will continue doing that section, and then there will be a week number 3 quiz due on that corresponding Wednesday. Okay. Are there any questions? That's all then for today.